The first topic for Senior 2 Physics is wave, topic 4.05. Wave. A wave can be described as a disturbance that travels through a medium from one point to another point. Also, it transfers the energy from one point to another point without transferring the matter. This is very important point. The first point is that the wave can create the disturbance in any medium from which it is traveling. But what is the main job of the wave? This is not the job of the wave to create the disturbance. The main job of the wave is to transport the energy in the very efficient way. And what is the efficient way in which it is transferring the energy? The efficient way is that it is only transferring energy without transferring the matter. So, wave can only transfer the energy without transferring the matter. That's why we can say that this is the most efficient way for the transportation of energy from one point to another point. Types of wave motion. The two main types of wave motion are transverse wave and the longitudinal wave. First of all, transverse wave. Move the free end of a spring up and down repeatedly. Do you notice that when the coils move up and down, the direction of the wave motion is perpendicular to the direction of the vibration? It means that whenever there will be a transverse wave, the particle displacement is perpendicular to the direction of the wave propagating. The wave motion is in the forward direction, whereas the periodic motion or the particle displacement is up down. So it makes out the perpendicular direction to the wave propagation. This is known as the transverse wave. The upper peak in the transverse wave is known as the crest, and the lower peak in the transverse wave is known as the trough. One more question. How can we generate a wave? We can generate any transverse wave by just using a spring. Tie the spring from one end of the ball and keep moving that spring and transferring the energy. You can observe the transportation of the energy there. The animation below shows a one-dimensional transverse plane wave propagating from left to right. The particles do not move along the wave. They just only oscillate up and down. Longitudinal wave. In a longitudinal wave, the particle displacement is parallel to the direction of the wave propagation. The figure below shows a one-dimensional longitudinal plane wave propagating down a tube. In this wave, you can see that the wave motion is in the forward direction, whereas the particle motion is also moving, oscillating back and forth about their individual position. And it is comprising of the two parts. The first point where the particles are very near to each other is known as compression, and the second part where the particles are very far away from each other, it is known as the rarefaction. Normally, compressions are those points where air pressure is higher than normal, and rarefactions are those points where air pressure is lower than normal. Compressions are also known as squashes, and rarefactions are also known as the stretches. The best example for the longitudinal wave is the sound wave, and the best example for the transfer wave is the light wave. And the best example for the transfer wave is light wave and radio wave. One more point, both of them belongs from an important family, and that is electromagnetic wave. Yes, it means that the speed of light waves and radio waves are same, and that is 300,000 kilometer in every second. Now, we are going to describe a wave. There are four phenomena that we need to clear for describing any wave. The first one is the frequency. The number of waves that pass by a point every second is known as the frequency. And the unit of frequency is 100 Hz. Let's suppose if there are 100 waves passing out a point every second, so its frequency will be 100 Hz. Or let's say if there are 100 waves passing through the point in 2 seconds. So in this case, we will divide 100 by 2 because we need to calculate the number of waves passing out the point in 1 second. So after dividing 100 by 2, we can say that the frequency of this wave will be 50 Hertz. Now you all can see in the figure high frequency, medium frequency and the low frequency. There in the high frequency there are a lot of vibrations passing out the point in the time period, whereas in the medium frequency the time period is same taking out by the wave as the wave was taking in the high frequency, but there are very least number of waves passing out through the point. Second phenomena, wavelength. It is the distance between two identical adjacent points in a wave. We can calculate the wavelength either in the transverse wave and we can calculate the wavelength either in the longitudinal wave. The distance between two consecutive crests or two consecutive trough in the transverse wave will be represent the wavelength, whereas the distance between two consecutive compressions or two consecutive rarefactions in a longitudinal wave represent the wavelength, and it is typically measured between two easily identifiable points and it is measured in meters. Third point, time period. This is the time required by the wave to complete one cycle is known as the time period of a wave. Or more commonly in the more simple words, I can say that how much time required by the wave to complete its one cycle. How much time required by the wave to complete its one cycle is known as time period, and normally it is measured in seconds. Last phenomena, the height of the peak from the central line or from the reference line is known as the amplitude. The height of the positive peak is known as the positive amplitude, and the height of the negative peak is known as the negative amplitude, and normally it is measured in meters. This is very important phenomena, relation between frequency and the time period. Time period and frequency are inverse to each other. It means that either if I am increasing the time period, the frequency will decrease, or either if I am increasing the frequency, the time period will decrease. Higher the frequency, lower the time will be taken by its time period. For example, you can see the two waves in the given figure and they both are containing 1 second time. For the first wave, you can see that there is only one positive peak passing out through that point. So one peak in 1 second, it's known as the frequency. So the frequency of the first wave is 1 Hertz. Whereas in the second wave, you can see that two positive peaks are passing out the point in 1 second. So its frequency will be 2 Hertz. So the above peak has the highest frequency, lower frequency, and the second wave has the highest frequency. But in the first wave, you can see that it has the greater time. It means that in 1 second, it is only completing one cycle. But in the second wave, you can see that two cycles are completing. There are two cycles are completing in 1 second, which means that 0.5 second for each cycle. So it has the lower time period, has the higher frequency, and the first wave has the highest time period and it has the lower frequency. So its formula can be written as T equals to 1 upon F or F equals to 1 upon T. This is the wave equation that we need to use for calculating the numericals or for calculating the unknowns in the numerical. Speed equals to frequency multiplied by wavelength. Speed should be measured in meter per second. Frequency should be measured in hertz, and wavelength should be measured in meters. Now we can easily solve the book examples as well. In the first question, we need to calculate the amplitude and the wavelength. And in part B, there are the wavefronts. We can use the line by drawing the wave. We can draw the waves by using the line, and they are known as the wavefronts. And the distance between them shows the wavelength of a wave. And in the second question, we need to calculate the different unknowns given out in the question. And in the third question, we need to just tell about the important wave phenomena that we have already discussed in this chapter. Thank you so much.